So let me introduce why PUF is so important for the random number generations. And let's begin with the question, what is a random number used for? Random numbers are fundamental building blocks of cryptographic systems and used to inject unpredictable data into cryptographic algorithms and the protocols to make the resulting data streams unpredictable and unrepeatable and virtually unguessable. Okay, so let's turn to page 15 in the slides. Okay, so the random number is very important cryptographic systems. So what is cryptography? Cryptography is an information security tactic, which is the art and the science of keeping messages secure. So how do we keep messages secure? Basically, there are three elements as shown in the page 15 of the slides. First is the authentication. The authentication ensures the person on the other end of the connection is who they say they are. Okay. And the second element is confidentiality. And the confidentiality ensures only the authorized person listening to the transaction is able to extract meaningful information. And the third property of security is integrity. And the integrity will ensure there are no undetected changes or interference to the transaction as it travels from the sender to the intended recipient. Okay, so because as we mentioned in the previous slides, the random number is very important in these cryptographic systems. So the random number are the fundamental to all the aspects of data security, since it can be used with cryptography to make data unrepeatable and unguessable. However, the strength of the security mechanism is directly proportional to the randomness of the number it uses. So as shown in the page 16 of the slide, you can see that there are three figures shows the effect of the randomness on the encrypted informations. So on the left-hand side, that's the original informations. And if the data is encrypted with the random number, but with poor randomness, then you still can vaguely see the data. And on the most right-hand side, if we encrypt the information with the random number, which has a very high randomness, then you cannot see that any information after the random number encrypt with the original plain informations. So this shows that even you have a random number, the quality of random number is very important. And later on, I will explain why our PUF can reach such high randomness random numbers. So traditionally, in general, there are two ways of generating random numbers. One is by the software methods. We call it the software random number generator. And in the modern computer program, the modern computer program can use software to generate a random number. We call it the pseudo random number. rather than true random number. Since a computer is only a machine dictated by human instructions, it will only repeat the few steps for the task we tell it to do. Therefore, computers alone cannot generate a random number, since it is impossible to generate something that is unpredictable by a computer. So software random number generation also requires a seed, which is used as an input to the algorithm of a mathematical computation to create pseudo-random number. So however, there are three disadvantages to use software-generated random numbers. The first one is a seed value is required to initialize the equations. And the second is the generated sequence of the random number will eventually repeat itself, which you can see in the page 17 of the slide. Okay. And the third, the random numbers are generated mathematically, and therefore it's not true random number. This means the software-generated numbers are unable to provide high level of cryptographic protections. So in page 17 of the slide, in the bottom, it shows that you need the seeds to input to the software random number generator. Then after the computer run the algorithm, then using the seed to create the pseudo-random number. So by doing this, you will see the random number to some extent. In some time, they will repeat the sequence of the numbers. So it is not really the true random numbers. So basically, in order to provide a very high security level, we have to turn to the natural physical world to extract something that behaves truly random by nature. From there, we can extract random numbers. So a true random number is something that is that a physical device produces, and we cannot know its value until it has been generated. So that's the first way. So in the second way, then we have to turn to the hardware generation of random number. So we call it the hardware random number generator. So in hardware random number generators, we generate a random number. We do not require a seed because they are not computed values and are not derived through a repeatable algorithms. So which we show it in the page 17 on the right-hand side. In this part, we have a path, and we enrolled the path to start to work, and then in the path, it will, after the enrollment or initialization, then it will start to create the random numbers, and I will explain how it does to create the random number. So, in order to do that, the next question is, what are the processes and the behaviors of the device we can measure that are really unpredictable? So let me give 2 examples. So you want to measure you are able to measure, but that is unpredictable. So, for example, we can find a random number by counting the number of passengers in an intersection every 10 seconds. If the number is odd, then we can set it as 1. If the number is even, then we can set it to 0. So after 2,560 seconds, then we can derive a 256-bit random numbers. So what's the probability to guess the correct numbers from the 260-bit numbers? So I did some calculation for everybody here. The probability of guessing the 206-bit random number correctly is 1 over 10 to 77. Okay, so 1 over 10 to 77 is come from the 1 over 2 to 256 because you have 256 bits, and every bit is you have a probability of 0 or 1. So probability to get everything correct in the 256 bit is 1 over 2 to 256. So after the conversion to the base 10 number is 10 to 77. And what does 10 to 77 means? 10 to 77 is 77 0 after 1. And we all know that 1 trillion is 12 0 after 1 is 10 to 12. So 10 to 77 is a very, very big number. So 1 over 10 to 77 is almost 0. So that means if you have a 256-bit random number and you want to guess it to the correctly, then if you give one guess to this 256 random number, then the probability is 0. Okay. And another example I would like to give is we can also measure, because we are looking for this random number can be generated on the chip. So we can measure the width of every 2 transistors placed aside. Even if the joint width is the same on the chip for the both transistors, but after fabrication, they may still have slightly different width. So based on their width, we can set it a 1 if the one on the left-hand side is longer, and set it 0 if the one on the left-hand side has a shorter width. Okay, so by measuring 256 pairs of transistors, then we can get the 256 bits of random numbers. Okay, so there are a bunch of examples I can give. For example, another example is you can flip the coins, right? And you flip the coins 256 times, and you can get the 256 numbers. Okay. However, for all these examples, it is important to note that for the example we just mentioned, they cannot be done electronics on the chips. And the second, the randomness is not likely enough. For example, for the passenger's case mentioned above, we may get a long stream of 1 or 0, depending on if the intersection is busy or not. What I mean is, if the intersection is busy, then you can get the 1 and the 0 mix, a string with 1 and 0 mix. But if the intersection is not busy, and you measure it every 10 seconds, then it will come out with the similar number for a while. And for the transistor width examples, because the patterning process may be biased during the fabrication, such that the transistor width on one side is always longer than the other sides. So in that case, then you will also get a series of long string of 1 instead of you have the mix of 1 and 0 for each bit. Okay. So the problems we really need to solve are the random number need to be electronically measured on the chip. So that's one thing. And the second is the randomness of the random number need to be high enough such that it cannot be predictable and repeatable. So in our invention, the NeoPUF okay, we extract the quantum link tunneling behavior of the electron tunneling through the thin insulator of the transistor's gate dielectrics, which is shown in the page 18 of the slides. The tunneling behavior is strongly dependent on the quality of the thin dielectric films. A slight difference in the film quality will result in significant difference in tunneling probability. And we measure the electron tunneling behavior of two adjacent transistor gate dielectrics. If the one on the right-hand side has a larger tunneling current, then we define it as a digital 0. And if it is small, then we define it as a digital 1. And we can generate 256-bit random numbers if we have 256 pairs of adjacent transistors. So you can look at in the page 18. Okay, so in the middle figure, and the bottom part of the middle figures, it shows the cross section of two transistors. And on the left-hand side is easy to tunnel, and on the right-hand side is difficult to tunnel. And that all depends on how many quantum well in the insulator dielectrics. So in the graphic, you can show if you have many defects. The defect means wells. Okay, the trap level is we call it also the quantum well, and you have many defects, then the electron can tunnel from the gate to substrate easily. And if there's very few defects, then the electron cannot tunnel from the gate to substrate easily. I think this is similar when we want to cross the river. If there are many stepping stones in the river, then we can cross the river through those stepping stones. But if in the river there's only one stepping stone in the middle of the river, then it's very difficult for us to cross over. Okay, so by using this mechanism, okay, the result is truly randomness, since the film is uniformly growing on the silicon substrate. And the difference in tunneling behavior of these two transistors are unpredictable. And the second is the tunneling current is electronically measurable. And the third is the difference in quality is randomly distributed, so that a high randomness can be achieved. So by performing the quantum tunneling behavior extraction, we are able to create random number for each chip to act as a unique hardware key, and which governs the security of the chips. Okay, so we have taken this PUF random number to build basic security functions such as the root of trust and the security coprocessor and the secure element to provide a new architecture for achieving high-level security. So both of our recent news release in cooperation with ARM and with Intel Foundry Service, respectively, focus on security solution based on our quantum tunneling PUF, NeoPUF, including the hardware root of trust and a secure coprocessor. With the proliferated cloud application that require confidential computing, the PUF-based hardware root of trust is extremely important in next generation CPUs. And ARM selects our PUF-RT, PUF-based root of trust, which is a flagship product of our PUF security solution to be the secure subsystem in ARM v9 confidential computing architecture reference design. PUF-RT is fully integrated, integrates key generation and secure storage, as well as true random number generator, which is indispensable for all the security operations. And this cooperation helps customers seamlessly apply security design at the beginning of the design when selecting computing cores. Looking ahead at the growing demand and the importance of security in the future for various applications such as AI, DPU, FPGA, IoT, automotive, etc. The cooperation with Intel Foundry Service is an important step forward, allowing customers who utilize Intel Foundry Services advanced process platform to directly import our security IP to meet the desire of secure supply chain and zero trust applications, particularly which is been emphasized especially in US market. Our shared vision is to provide the global customers with the best chip security while enjoying also the high performance advanced process at the advanced process nodes. Okay, so that is my presentation and the introduction for the importance of PUF on the random number generations and which is the foundation of the information securities. Okay, thank you.